Today we have Omjyoti Dutta. He is from the ICFO. He did his PhD thesis in the Arizona University in Tucson with under the supervision of Pierre Mestre. And then he moved to Barcelona to the ICFO Institute, where he has been there for around 4 years. And he is working currently on cold atoms. And he's going to talk about Hubbard models, I think.
The magic level state.
Yes, sorry. I forgot that he's in the group of magic.
Thank you, Manuel, to give me the chance to talk here. So what I will talk is about basically Hubbard models, but in the field of ultracold atoms and molecules and so on. The first thing is I sometimes speak very fast. If I speak very fast, then say that please slow down. This happens automatically. So the first thing is the outline of the talk. So what I will tell is basically the basic things. So in the field of ultracold atoms, I think hopefully all of you are not from this field or subfield. What we do, I mean, one of the main area of research is that you prepare atoms or molecules, let's say, or try to prepare them in sub-micron temperature, and then you want to trap them in an optical lattice, which is basically you put some lasers, you create some periodic potential, and you try to trap these atoms or molecules in this kind of lattices, and then you try to model them. I mean, why you want to do this? Okay, there are some reasons, which is one of them is one of the popular reasons why people study this is to emulate or simulate certain kind of condensed matter system, where the analogy is that this optical lattice is not exactly but like crystals in solids, and these atoms or molecules are like, not exactly, electrons in these crystals in the solids. And so you try to emulate or simulate physics which are there in condensed matter, but not only that, you can want to do much more because of the fact that you have atoms which are in sub-micron temperature. So you can basically control them very well. So, and also you can control how you create this lattice by using these different kind of laser geometry. So one want to use this to control and create different kind of states of matter at the end of the day. And to use it, okay, I don't know, you can use it in different things. The proposals around quantum information, making quantum computers, let's say, or making some kind of gates and all those things. So the question now is, so you have this model, you have this lattice, optical lattice, you have atoms or molecules in them. Now you have to write, what these kind of things follow. And the usual model which people use is these Hubbard models, which is people know from long time in the condensed matter system. And this is the usual model people write, and then they try to find the phases and these. Now, so this is the first thing which I will describe, and which most of the people know for a long time. The second thing what I will say is this, that but is this true? So when you write these atoms and molecules which go in the optical lattice, and this is the usual way of describing then using Hubbard model, if this is true. And if it is true, then how good it is true, this kind of standard models, okay, how good it is, or what kind of extensions you have to take into account actually to simulate these atoms, because if you want to say that, okay, we are simulating these atoms or just simulating some system, so then you have to know the model which we are simulating, and the point is that, so that's why you want to know that what we are simulating at the first point. So this is this part of the thing, and then I will say that, okay, I mean, if you do this, if you write the model with some extension of the standard things, what changes? No one can say that, okay, if nothing changes, then it doesn't matter. But the point is that then I will show in the case of these dipolar fermions that things changes and some nice phase can come as a result of this. At the end, I will talk about the conclusion and future and these things. So first is what is this Hubbard models? What we will say in the context of ultracold atoms or molecules. So we have some laser potential, and then we trap these atoms in this laser potential. So let's say it is in this local trap, let's say. Now, these atoms can quantum tunnel to the next, this local trap. And this is one effect. This is a single particle effect in the sense that if you have just this lattice and if you have these atoms, they will go from here to there. And this is denoted by this tunneling term. And then if you put two atoms in the same place, then what can happen is that they can interact between them, no? Because this atom, for example, let's say with van der Waals force. And because of this interaction, if it is repulsion, then these two atoms will have some energy because of this interaction, which is at some place, which is little bit above this level, let's say. And this interaction we denote by this term. This is depending on the density, where these B's are this creation or destruction operator for these atoms, and these Ni's are the density of the atoms in each site. And here I am talking about bosons. That's why you can have, say, two atoms in the same state. Now, this is the most famous model in the field of ultracold atom. Okay, this is the usual Bose-Hubbard model, as we call it. And this describes basically then two terms. One is the tunneling of these particles, and another one is the interaction. And the assumption now, when we write this, the assumption which goes into this is this. That as you see, think of this as small, like local harmonic oscillators. Then they have the energy levels, no? And assumption is that this interaction is not so large that these two atoms don't want to be in this small, the lowest level, but want to go to the higher level. Okay. So this is the assumption, which says that the interaction strength divided by this the excitation energy, let's say, to the next level is much less than 1. So this is the important assumption when one write this kind of Hubbard model, and they say that okay, we write it in lowest band approximation, and the time binding means that we only consider tunneling only to the next site, let's say, if you want to call this a site, then the next site, not to the other. And now the phase of this is known. So you can have two kind of phases, let's say. One is this, say you have one atom per site, let's say. If you want to put another atom here, you need to put this interaction energy, no? So to put this atom, you need some energy, and if the tunneling, which is this J, doesn't give it, then you don't put it there. That means that you have a state where each site has a specific number of particles, and which is, let's say, this. So if you plot them as a function of this tunneling divided by the strength, for low tunneling or high interaction strength, each site can only have fixed number of particles. This one is one, this one is two atoms per site, 3, and so on. No? But when you have lots of tunneling, means this can go there with high rate, then doesn't matter if there is some energy, no? It will go anyway. And this is the state where an atom can delocalize over the whole lattice, and this is the superfluid state. This is so this was first done in the 1980s, no? This kind of model and the prediction, and this was seen in ultracold atoms, I think 2000 or something in Germany. Now, so this is one model, let's say, what people use to do this kind of things. The second one is, of course, another thing which is with ultracold physics you can do.
You don't have a stage in which you can have half of the wells with double and half with one. You only have this stage in which they are either well. Normally it is, but I mean it can happen depending on the way you take the interaction and this, the way you take the lattice and this. But normally, if you have the usual lattice with tunneling and this U, then always you have this or this. I mean this or this, sorry. So the next thing is, okay, so the thing is, as you see, no, here the main thing is that the interaction, it's only short range. What I mean by this is that it's only important if they are in the same site. Now there are another kind of interaction which is one of the big point of using this ultracold atoms is this, that there are atoms, let's say chromium or dysprosium. These atoms have a large magnetic moment, and because of this, what can happen is that if something has a large magnetic moment, this will have some dipole moment, something, let's say, no? And if they are far apart, still they will interact because of this dipole-dipole interaction. So this is the part what we are talking about. This is for atoms, but now people are trying to create molecules, no? So if you have, say, heteronuclear molecules, for example, rubidium, potassium, then already you have two different charges in one molecule. So if you put two molecules there, they will interact between themselves by this long-range dipole-dipole interaction, because each of the molecule you can think of like a dipole. And this is an important thing because in normal condensed matter physics, there are electrons which can provide this long range interaction, but the interaction is screened. So effectively it is short range. So in this optical in ultracold atoms or molecules, so this is the important fact that you can actually create a system where there is long range interaction in the sense that particles, even if they are in some distance, more than say 1 lattice or something, still they feel the effect. So this is the second point, which is another thing. So what we have here is this. We have a lattice and we have these dipoles. Here we have talked about molecules, let's say. So they are electric dipoles. And you put electric field perpendicular to this plane, okay. So this is the direction. So what I mean by this is that, so now if you have two dipoles which are pointing up in this plane, no, then they will always interact via repulsive interaction. So this is the situation that, okay, you have molecules which interact, interact with this via this long range interaction, which is repulsive. And if you have low filling, we can do effectively hardcore, means that one side cannot have two particles. And then you can write another model, same thing, okay. So same tunneling, but instead we have some interaction, now again density interaction, which depends on how far they are. So one particle here, one particle there, still they will interact with something. So this is another another important model for the field of ultracold atoms, let's say. And because one of the reasons is that this can have interesting phases. And so this is a study from this paper. So what you see here is there is a chemical potential, and there is again the tunneling, no? And divided by this nearest neighbor interaction. So that means, so here what we have here is this. So let's say your tunneling is small than this V, no? So this V is the interaction between this side and the next one. So what will happen, no? If I am here, I have some interaction. If I am there, I have less interaction, no? Then I don't want to come here, I want to be far. So they want to be as far apart from them as possible when there is very small tunneling. So this is the situation where you have half field system, means number of lattice sites and number of atoms or molecules is half of the number of sites. Then what you have is that each atoms don't want to be next to each other, so they avoid. And this is the structure they form for low tunneling, because okay, they cannot tunnel, they want to go to the next side, they have to cause this nearest neighbor interaction. This is V. For, I mean, not only that, if you go lower filling, means 1/3 or 1/4, means that you have 1/3 atoms of the 1/3 number of sites is filled. Then also you have the similar thing for very low tunneling. You have another crystal structure, means that if one of atom wants to move, it has to overcome some energy, and that's why you don't want to move, let's say. So they again, this is kind of a stripe where in three sides one of the atom is there. So in three there is one atom, next three one atom, and like this. Same for 1/4. Okay. So that, but then the interesting thing is this: when this side is the high mu is the side when you have this crystal and then you dope with particles, or this side when you take some particle out of it.
What are you following in the y-axis?
This axis?
Yeah, what is this?
This is the chemical potential. This is okay. So what we do is that, okay, the number of atom is this is when you try to minimize that. This is the Lagrangian multipliering things. What is basically this controls basically the number of atoms more or less in the system, because when we try to solve this, we cannot have, if it's not an exact diagonal relation, we cannot have fixed number of particles. Okay, so this basically take care of how much particles more or less you have in the system. So in an experiment, for example, let's say in an experiment, if you have a fixed number of particles, then you will be somewhere here, okay, depending on what density you have. So this is okay, but in an experiment, we have, I mean, it is little bit different.
So this phase diagram, what is the order parameter here?
So here the order parameter is the checkerboard order parameter, which is the number difference between this side and the next.
The number, sorry?
The density difference between this side and the next side.
So inside this area is fixed.
This is fixed. It's like 1 0 1 0 1 0. Well, more or less. In the mean field, it will not be around 1 0, but then in the Monte Carlo, it will be like 1 0 1 0. And okay, now in upper, so upper left means more mu, and here it means that there is more. You dope this with more number of particles. So you dope particles, and here you take some particles out of this thing. What happens then is this, that if you include the fact that not only nearest site, no, it interacts with all the other sites because of this dipole-dipole interaction. Then what you will get is that you get something what is called a super solid. I mean, what is this is not is this that you still have this structure, but still you see that there is some superfluid density, means there is some coherence of diagonal coherence over the whole lattice. So if you think of this in some kind of mean field way, what you will see is that if you have a superconducting order parameter, some order parameter, which superfluid order parameter, which says that then you will see that it has some value here, some low value here, high, low like this. And so this is okay. This is a very highly debated state, no? Because in condensed matter, this kind of state, existence of this kind of state has debated for time immortal, and still people fight. So, but okay. But the thing is that, so here he says that okay. So because of this long range interaction, we can simulate or we can get this kind of states which has both this crystalline order and the superfluid order together. So, okay, this is the point of this slide. Now,
sorry, in these phases, the dipole moments are always collinear?
yes, they always, because we put a electric field to make them all point along the same direction. So then, so as you are right, so if there is no electric field, no, if you take them infinitely close, they want to flee, because this decreases the energy. But if you have a strong electric field, then they cannot do that. And also they cannot come so close because there is a lattice in between.
It's in a strong field.
It's it's like to polarize it, you need strong field, kilovolt per centimeter.
But the field is not in the Hamiltonian.
No. So that's why I said That's why I said that when I first started, I said there is polarized molecules. That means we have electric field which is very strong, so that all of the dipoles point to it. And one can calculate, no, like this lattice side, the length of this lattice is around 500 nanometer, and along this, the interaction strength is, you have to have this electric field stronger than the interaction strength between the dipoles, so that then it will not move. It doesn't matter. Even if they come closer, they don't want to be like this. But okay, but this is not always true. Okay. The second thing, of course, is we have atoms, we have dipolar bosons. Now we put fermions. No, the thing is same again. We have again for the fermions, we have again the same thing. But now we have Pauli blocking, which means that this one particle will not come to the same site at the same level. It will not come at the same energy level because of the fact that they are fermions. But the Hamiltonian is against the same. We have some tunneling, we have some again long range interaction, and dipole-dipole interaction, which is 1 by r cube. So this is the phase of this. Again, I mean, this looks very complicated, but it is really not much complicated. The point is this, that here you have filling now, which is the number of atoms divided by the number of sites or molecules here actually. And this areas D, B, B, C, D, whatever it is, they are just different kind of crystalline structure depending on the filling. Okay. For example, this 2B is like a checkerboard, as we saw before. One is filled, one is less filled, another is filled, another is less filled. And
in the previous transparency or slide, you mentioned dipole bosons, right? And the next one is dipole fermions. Okay, sorry.
So the only difference is that the two will not come at Pauli blocking. I mean, because of the fact that they are Pauli blocks, so they will not come to the same side. And this dash size is a typical thing for fermions, which is that if your filling is not commensurate, like this is like 1/4 something, what you can get is that you can get a phase separated state. That means that one kind of crystalline structure in one place, another in some another place. And this, okay, if one does mean field theory, you get this. And there are no studies which goes beyond mean field theory, because fermions are very hard to do theoretically. Exactly, like there is no Monte Carlo for fermions in general. Okay, in some specific case maybe, but in general no, nothing. So this is one of, okay, this is again the more or less the same phase diagram as before. And there are other ways also to do these things, which is that what you can do is that there are dipoles, no? So they are like this, but then you try to control their rotational spin. So they can rotate along their thing, no? So what you do is you put some laser, you put some microwave fields, and you try to control their rotational structure. And by controlling this, you can kind of map out some spin models. And this was the proposal for this, that you can kind of controlling these rotational states, you can get some kind of spin Hamiltonian which have this basically charge density wave or phase separated or superfluid structures. Okay, but so this more or less is the thing which I wanted to say of the Norman Hubbard model. Okay, the point of these slides is that these are the usual model people use when they try to describe these systems. Okay, and I want to say that okay, the problem is that this dipolar fermions as a molecule and dipolar bosons, but molecules till now they are not available in the experiment. They are available, but nobody has trapped them in a lattice and went to low temperature. That is the problem till now. But people will do it very soon, I think. This is the situation. Now the thing is that so I want to now tell, okay, these are the diagram and everything and all that, but these are the models, which describe these systems. This is the point now what we will go. And to do this, first I will talk about one experiment. So this experiment was done in Munich. What it was is this, you have some lattice and you have some atoms inside it, depending on different number of particles. Now you can think of this, if there is one atom, then you can think of this like this, it has a wave function inside it, which is like a Gaussian, let's say, for example. This is not true, but you can think of it like this. When you put two particles, because they interact, if two particles interact repulsively, they don't want to be together, they want to be far apart. What that means is that this wave function of this particle gets little bit broadened. And what it means that the interaction, which is that effectively 1 over volume, gets lower, because if the wave function gets broadened, that means the volume increases, that means the inverse of the volume decreases. So this is, so what it means is that, so if you have two particles, you have some width, then if you have three particles, you have more width, because it's interacting more. If you have four, you have much more. So the interaction will accordingly be lower, not totally lower, but it will be lower than what it should be. So what they did is, they made a system like this and then try to do an interference. So if it has only one frequency, that means that if there was only one interaction, there is no broadening, then you will just see one pattern with one frequency, which is given by this interaction strength. But if there are many, if that depends on the number of particles, then you have different frequency, because depending on the number of particles, the interaction strength kind of changes. So what they saw is that this basically, that as they do this, they see not a single peak structure like this one, but this blue one. That means there is many different frequencies which are inside. And this was one of the first experiments which basically said that, okay, like the way we write these Hamiltonians may not be right, because there is a change in interaction depending on the number of particles it has. And this is one of the first experiments which basically says that, okay, we have to take into account more things probably. And there was another experiment in Hamburg. So this experiment, what they did, okay, the first picture is, this is absorption images. Okay, what you want to know is that if there is a peak, means there is a condensate. So this is the height of this lattice, okay, this 25 recoil, let's say, or 20 and this. As you decrease this height, what happens is that the tunneling increases, so you should go to the superfluid state. So if you do this, you get the superfluid state which is given by this peak, which shows phase coherence in the system. Now, what they did is they mixed these bosons with some fermions, and what usually one expects that if you put fermions, then the effect of these fermions on the bosons is kind of, it imparts some attractive interaction between the bosons. So it basically decreases the interaction. So one should expect that you should show this phase coherence even for higher lattice depth, or higher lattice depth means depth of these things. But nobody saw that. They saw it even later, because here there is a peak you see, but here there is no peak. So that means that there is something going on which is not taken into account on these things. So people have done lots of experiments on this, and all of them have similar things. So the answer was this, that again, that if you put a fermions in a lattice and if you have some bosons, if the fermions interact with the bosons or attract in their case, then they make the lattice effectively deeper and deeper for the bosons. So the bosons see a lattice which is not the original wall but something which is different, and this depends on the number of bosons or whatever is there in the trap. So they use this, and they again use the same kind of effect that the wave function kind of changes, and they can explain this effect that actually there is this effect of this interaction which depends on the number of particles. So now I come, so what are these effects? So now I will tell you what kind of effects these are in the first place. So when you write this Hamiltonian, first you have this interaction. There are 4 operators, field operators, they interact. Now when you expand them in the corresponding basis, you get something which is like this, where these different things are the energy levels or orbital levels. And you have this term, this is the interaction, but it depends on what orbital the particles are in. Usually we assume that everything is in the lower one, but actually it's not true, because if you look at this, every level is coupled by this. So to find the energy, one had to diagonalize this whole system, by taking into account the whole thing. And this means that you get an interaction which depends on what is the population of other levels, depending on this term and the interaction strength. And then automatically the strength depends on number of particles, because if there are 2 particles, there can be some distribution. If there are 3 particles, there can be some other distribution. So the effective energy of the system changes, and that means that it depends on the number of particles. And this is a very simple thing that people never took into account. And this is the first thing. The second thing is, which is the most important thing for me, which is there can be tunneling which comes from the interaction. What I mean by this is that there are 2 particles on same side, they interact, they are interacting. Because of the interaction, 1 particle can go there. This is just scattering. 2 particles is there, they interact, they scatter to another place. And this, you can think of this as a tunneling, because 1 particle is here, because of the other particle it goes to the other side. And this also people never took this into account. And the second thing is that there can be another kind of transition where the same thing happens, like there is interaction and it goes to the side but not to the same orbital with some other energy. So there is maybe p orbital in this case which has 1 node. And this is very important, because this is a term which you never have if you have a single particle Hamiltonian, because single particle Hamiltonian, the way you get is you have the lattice, you diagonalize it, then you have the eigenstates, they don't mix with each other. So usually you should not have that. Because of this interaction, they can go to any place basically, it doesn't obey almost anything. So all this kind of tunneling term is also there. So to write the Hamiltonian, you need to take into account all these things. And what you get at the end of the day is, depending on what number of particles you have on other side, on 2 different sides, your tunneling will change. So your tunneling will have 2 terms, which depends on the number of particles which are on the 2 different sides, between which there is tunneling. So this is the important thing, and then you can plot. Some people can do calculation, and if you plot, you will see that here is the interaction strength, the scattering length, the scattering length, and here is the different tunneling parameters. Like 1 particle to 2 particle, or 3, 1, and all those things. You can see that we plotted it as a percentage of the ratio, where if you don't take this into account, and you will see that all of them changes. Some of them changes a lot. And this one is the interaction energy. And this also you see that it changes a lot as a percentage of, this is like 20%. 20 means like 20% changes. So this is 20% changing from the effect if you don't take this into account. So this basically says that all of these things as effect, a good effect. Now the question is that, this has effect, but if it doesn't change the phases, then it has effects. So the second question I will talk now is, if this can have nice effects, this kind of effect can even change the phases, the structure of the system. And this is, before I do that, actually this I put it for here, because here I think many people do this nonlinear sciences. So this kind of tunneling term, one can write it like this also, where you have the tunneling, you have the usual tunneling, and you have some factor which depends on the density. And this, you can write this as the usual tunneling term, but where the operators don't obey the usual bosonic relation, but they have some gamma, which depends on the density. And this is, people know this as this Ablois-Laddick model. And this kind of models are integrable, and there are solitons which are solution of this model. Like one of these things I took from this paper in the old days, where they have a harmonic trap and they have this lattice but in 1D, and they can see the trapping of a soliton and they're moving. So this is one change, because if you have any gamma, then you know that your system has a soliton basically. So any of these states. So now the second part is what I will talk about, especially the dipolar fermions in optical lattice. I will choose this because this is one of the places where it is hardest to see this effect, because you need two particles at the site to have this interaction which can show this effect. If two particles doesn't come to the same site, there is no effect. So, and the fermions, they don't want to come, because they are blocked by the Paul principle. So here what we have is this, that again the same system. We have some optical lattice which is some periodic potential, and the dipoles are polarized in the z direction, which I plot here. And these are the harmonic trapping along the z direction, and these are the levels. So the approximation is this, that to put energy, you need your energy level, energy gap in this x and y and this direction has to be much more than the interactions, which is some numbers, but the point is that it is true that the energy gap in this xy direction or in this z direction is much stronger than any other interaction. But the thing is this, that if you put two particles in one of this z direction, what we will see that the property entirely changes. So here the black line, if these two are bosons, then this interaction which I plot here as a function of this trap strength, that they are always repulsive. They are attractive here, but most of the time they are repulsive. That means that they will not come together. But for fermions, they basically are attractive for always. And this region is because the fermions, they always have this exchange interaction between them. And because of, if they are attractive, what it means, they want to come. The moment they overcome this energy gap, they will come together. So this whole idea of Single-man approximation and everything breaks down. So we have to start from the beginning again. So this is the point with dipolar fermions, that everything, this kind of approximation that we have only single band and everything breaks down. Now what happens if these two come together? This is the point. So here I just will show one of this picture, which is the number, this is the interaction strength as a function of this trap strength, and what you will see is just the number 1 curve, which is the important part here, which is the on-site interaction have two particles on the same site, one is at S, another is at this PZ, I called it here, and this is attractive, there is a negative sign here. And then you can have these other curves are, these 2, 3, 4 are basically the nearest neighbor interaction between different species, means the different S orbital or PZ orbital. So the important point is just this one, that this is very strong and this can be attractive. So the next thing is this tunneling processes, which I told before. So now the chance that two particles can be on the same site, so because of this interaction, this can tunnel to the next site, let's say this orbital, which is given by this one, and this one I plotted as a function of this J0, which is the usual tunneling strength, and this D, which is the dipolar strength, let's say, and this is very strong. This is 2 times, 3 times, and if your dipolar strength is usually maybe around 5, 6, so this is actually very strong. So to do this kind of thing, one have to take this kind of effect into account, even if this can take you to an energy level which is different, which has a different energy than what you started. So the others, these are the other tunneling terms which can come. These are just to show that this doesn't take into account. So yes, so what we have, the important term now is this then, that we have two particles on the side, this one can go to this, which is some higher energy. But then if there is another fermion here, it can come back, because this needs the interaction to go anywhere, If there is no interaction, it cannot go. So now this will give a second order tunneling term, which is given by this 4, and this is with respect to the usual tunneling. So this is strong, and so the point is this, that then these two, that two particles can be on the same side because this one is, this interaction is attractive, and the long range tunneling, there can be a long range tunneling, means that one particle is here, two particles are here, and this particle can go to this side even if nothing is there because of the interaction. And this can have dramatic effect, no? Because in the other models you cannot have this kind of things. So now what you do is that you try to find the ground state, no, again. So what you do is you plot them as a function of this trap strength for some filling. You take some particular filling, and here is the state we saw before, which is one particle is filled in every 3 sides, which is 1/3. This is the normal state people expect. When you have very small trapping, what it means that if 2 particle has very strong attractive interaction, then they want to be always together. They will act like a boson, no, because they always want to be together, 2 fermions. But in intermediate state, which is the important part, where you can see that there can be these fermions which follow a checkerboard pattern of 1 fermion in every 2 sides, then nothing there, 1 S fermion in every 2 sides, then nothing there, like that. But there can be some extra fermions which will go to this PZ orbital. And this can have a important effect, and this is the point, that because now you add tunneling to this side, okay. So we have some particle which is here, this PZ particle, that can go to the another one without anything, no. So this can tunnel here, but this cannot tunnel here because there is no particle. So you have situation where this can only tunnel this way, these particles can only tunnel in this side, this particle can only tunnel in this chain. So what is this is that, of course, it increases the stability in the sense that particle can tunnel, so the system is stable in this structure. The second thing is that it reduces the dimensionality of the problem, no. The problem started with this 2-dimensional problem, but now because of this inherent structure, it became a effectively 1-dimensional problem, where each of these PZ particle will all be moving in this direction. And this one way to study these things is what you do is that you write an effective 1D model or 1-dimensional model for each of them, and then you act the dipole-dipole interaction between these particles, because it's still there. And this you can do some way, anyway. There is some way to do it, which is you say that, okay, because it's a 1-dimensional system, each one has some Fermi point, and around that Fermi point you calculate the density fluctuations. And these density fluctuations can have some phase, and these are this θ1 and θ2, and these density fluctuations also have bosonic characteristics, because you can create a particle and a hole together. And then you write the motion of this kind of phases, which has some velocity which with the move, which is the sound velocity of the system, and they have some coefficients which comes from the interaction. And but this is the only thing one needs to actually take care of at this point. And what one sees is that then what we do is that you include the interaction between these different layers, which is basically this term L and L+1 are 2 different layers, and you plot, no, and there is some dimension one can calculate. The main thing is this, that if this quantity, no, is less than 2, then this system is stable. That means that what we described, that you have a 1D system effectively where every particle are only connect to one single chain. This picture is stable. But if we go to higher density, what happens is that it goes more than 2 and less than 2, and then because of this interaction between the chain, this kind of motions become unstable, and the system go again to the charge density wave or this kind of checkerboard state what we are talking about. But so in this regime actually then we see something which is called a symmetric metal, because of the fact that you have this tunneling or you have this conduction in some sense in one direction, but in the other direction you have no conduction, it's crystalline order. This is kind of a noble phase of matter, because this is a 2-dimensional example of a non-Fermi liquid, in the sense that if you have a 2-dimensional system, you always have this checkerboard or kind of Fermi liquid, in the sense that you have these quasi-particles which behave like a Fermion. But in this case, the whole nature changes. That you have quasi-particles which doesn't behave like a Fermion, it's kind of behave like a boson, and you have this 1-dimensional conductance.
What selects the direction of propagation?
This way. So this PZ particle will propagate only along this S sides.
You can also have propagation along the vertical direction.
No, but the vertical direction it cannot propagate, because to propagate in the violet first, this PZ particle cannot propagate, because to propagate it costs energy.
Yeah, but there will be another state which is the rotation of this one.
Yes, okay, I know. There are two configurations. One is along this X, but another can be along Y. But when you do an experiment or something, by fluctuation you will only choose always one of this configuration. In a very big lattice, there can be regions with one configuration here and another configuration somewhere there, which are the domains and these. But not a very big lattice. It will be this kind of. I mean, this can be this, or this can be the other one there. So this I will finish because I think already more or less 40 minutes. So the thing is that so what the main point of all those things, no? At the end of the day, the main point is that this Hubbard models, whatever is doing this, when we are doing this physics with ultracold atoms, let's say, no, higher than always have a very interesting role to play. And most of the interesting thing is that they can have a tunneling which comes from the interaction basically. But this can change the phases, and I mean this was true for fermions. For bosons also we did, and we can see phases which is like this checkerboard is the usual phase I talked about, always this crystalline phase. But then you can have situation where these pairs, two particles can be on the same side and they want to move always together. So this kind of pairs of fluid can come, for example, and there are actually, I mean this field is, I mean this kind of extension in Poltadon they started, I don't know, maybe 3, 4, 5 years ago, no? For condensed matter, they are there for some time, a long time before, around 1990s, to explain some kind of superconductivity, but which they could not, and then it more or less went away a little bit. But for cold atoms, this kind of things comes at first, and we have much more different terms, okay. And the physical effect is that this can actually changes the physics we are supposed to study. If we can control them, we can probably create some very nice properties of matter, which is not possible to create for, say, usual solid state system, let's say. No? And so this is the point that, and for experiments, one has to take this kind of terms into account, because even if they don't change the physics, they changes the where you want to expect something. No? If you want to expect to see some property at this point, because of these things, this point shifts already. So you need to take care of all these things when you want to, and that's it. Thank you for listening.
Questions? We have priority for students to make the first questions. There were already some questions. But if no, there are more questions from there.
You're talking about this atom system comparing with condensed matter, but how many atoms can you have in a lattice like this?
Okay, I mean the density in usual trap, there are I think 10 to the power, say for a 2D trap, if I remember, there are 10 to the power 12 per centimeter square.
Sorry?
10 to the power 12 per centimeter square. So this is much less than a 10 to the power 20.
The number of sites in one of those lattices?
The number of sites they can do, I think still there are like 100 cross 100 or even more. This they can do a lot.
To theoretically obtain this phase diagram, what kind of
this one. For this one, this one we did in 1D. We used exact diagonalization, and then this, and then we use this what we call this matrix product states method.
I have a related comment to this. Thinking of a finite size system, besides these phases you have discussed, can you also have edge phases? Or
yeah, so for example, if I go back to the first part of my talk, no? I just need one phase diagram. That's good, a good phase diagram. This one, let's say, no? So if you have the things in a trap, but that if you have the lattice and actually all the time we have some trap, what happens is that you can think of trap is like in each side the chemical potential changes. Then you will see in a trap, say in the middle of the trap, maybe you can see this phase, no? But as you go down, you will go basically outside the trap, because the trap depth decreases, so kind of the mu also decreases, and within local density approximation also. And so you can go, so in the middle you can kind of may see this phase, but when you go outside you can see this. So in the people who do experiment not on this, but with superfluids and these things, what they see is that in the middle they have see one kind of this Mott insulator, say n equal to 2 Mott insulator, then they go out, maybe n equal to 1 Mott insulator, And so what I mean by this is, so as you go outside the trap, you can start from here, and first you have Mott insulator in the middle of the trap, then you have some superfluid, then again you have a Mott n equal to 1, then again some superfluid. So that's where you see.
And when you say the trap, you don't mean the individual trap?
No, I mean the whole trap. Whole one.
So if not, we can take